science. If you don't like this, then it means it will be difficult for you in the graduate computer science. You probably should do something called applied computer science, because this is theoretical. So if you want to go into advanced theoretical computer science, say do a PhD in computer science, then you need this. This is the first thing they will ask. And then you have two other graduate courses at FIU, three in fact. Theory of Computation 1, Theory of Computation 2, that takes off where this is and repeats some stuff. And then computational complexity, which is our last chapter in this course. So you have three graduate courses that are like this. So this is why this course is good. But if you want to do theoretical computer science, if you want to do practical computer science, you know, you want to do gaming and whatever, then this is useless. I'm not going to lie. This is not going to make your gaming better, but it's going to give you the foundations of theoretical computer science. But let's not waste more time. I have material to cover, and so let's talk about this. Okay, so the pumping lemma we had seen. Okay, I give you three problems. We saw this. So first of all, I saw the easiest example. I saw this. This is a non-regular language. And I'm repeating now. Why? Because it's important to repeat sometimes so you can see the trend. So I won't go through the whole proof. But here we said, hey, you know what? I skipped the loop, right? So if we must have a loop as shown below, and then we skip the loop. So I underline that. And you're thinking, okay, yeah. You did that. You skipped the loop. Now what happened? We got a contradiction, right? Because we got something that was accepted, what was not supposed to be accepted. Because once you say this, there's a machine. Once you are regular, suppose this language is regular, there's a machine. And the machine is supposed to accept only the things in here. And then you show the machine something it's not. This is just like when it's square root of 2 proof. Square root of 2 proof says that, you know, you get it in lowest form, and then what you do, you get a contradiction to say it's not in lowest form. P upon Q, square root of 2 equals P upon Q. And you say, oh, you do some mumbo jumbo, and you say 2 divides P. And another mumbo jumbo, therefore 2 divides Q. Therefore P and Q have a common factor, but they were chosen to be not with a common factor. Contradiction. You're thinking, I don't like that proof. Well, that's what proof is. And that's what you do in discrete math. And that's why I keep telling students, if you did discrete structures, we are not going to stop you, but you shouldn't do this course, because discrete structures doesn't prepare for this course, right? But discrete math, it prepares you more or less if you did it well, and you did well. Now, we skipped the loop, and we got a contradiction. And we said, okay, therefore the guy is non-regular. So we are thinking, good. Then we had another language, L2. And we said, okay, loop again. Now, if you notice the loop here, I was showing you every little thing, how you go QI. Here, this is how you do in the exam. You're like, hey, there's a loop there between here and here, right? And from here to here, I didn't see anything, right? But I said between here and here, because there is n plus 1 things and there's only n different states, you must have a loop. That's why I pick A to the n. So you're thinking, oh, and that's why you got your loop. Now, somebody might say, hey, wait, professor. If you got a loop here, shouldn't you have a loop here? Yeah, there's loop here, but we don't care about these loops here. What we care is this loop. Now, if you skip it, like the previous time, and nothing, you wouldn't get a contradiction. But if you write the loop twice, you see, because if you skip it, you will get something smaller, and you'll get something smaller than n, and you get n minus j, or whatever, and you get n, and you're like, no contradiction. But if you don't skip it, and you write it twice, you get n plus j, and then this is supposed to be smaller than that, smaller than or equal to. So you're thinking, oh, you have two techniques here. Either you skip it, skip the loop, or you write the loop twice. And that's the whole idea. Skip the loop or write the loop twice. And you're thinking, that's the secret. So all the problems in number 6, in all the exams, it's all about skipping the loop or writing the loop twice. And you're thinking, okay, I learned the technique, but I don't understand all your mumbo jumbo about Q0 and Q2n. Well, Q2n is the total length of the string. And Q0, like how I put Qn here, it means from Q0 to Qn, you process A to the n, because you need n plus 1. So you're thinking, hey, wait, Q0 to Qn. Oh, yeah, that is n plus 1 state, because 1 to n is n, and you have a 0, so that's n plus 1. Yeah, that process is A to the n. Okay, I get that. And the B to the n, you get n more states, and you start here, and you go there. From here to here is n plus 1 states too. So you have a loop there, but we didn't the loop I'm not showing because it's not relevant. We are writing this loop twice, and we're ignoring that loop and doing whatever it says here. And we got our contradiction. Now, we got a third example. This is like, okay, I want to know you don't have A and B. How will you get a contradiction here? Now, if you have A to the N, there is no contradiction. A to the N is A star, right? Or A to the K, that's A star, that's regular. But if you have A to the K squared, you're thinking, I want to see how you will get a contradiction here. And that's why this example, which was the last thing I think I did, you're thinking, oh, well, professor, you went all the way here, and you took n squared, and now I see you took this crazy thing here, a to the n plus 1 squared, which is a to the n squared plus 2n plus 1. You took that as your, you didn't took a to the n, b to the n. So every time some student think, hey, I notice he's always taking a to the n, b to the n. He took it there, he took it there. But if you do the exams, you will see you can't do that because the problems are changed. I don't give you this example in the test. I give you something slightly different, right? I give you k is greater than or equal to 2n, k is greater than or equal to, like here, k is greater than or less than or equal to 2n plus 1. You're thinking, oh, he changed it. But you have 19 of those questions. And so you see the trick after 2 or 3. But after 5, for sure, you see the tricks. And it's only 2 choices you have. Get a loop and skip it, or get a loop and write it. Every problem is like that. And so some students like, but professor, that's the hardest proof. I agree, but it's number 6. Get the first 5 right and then write some BS, you'll get some points. And you like, but how will I get the first 5 right? Okay, when you look back at your first exam, no problem there was beyond your reach. Every problem you've seen before. And, so for the students who are thinking, well, look, this stuff is hard. Well, I don't know. I wouldn't say it's hard. I would say it's strange, but not hard. It's unfamiliar, but that's why you play around with it. So, I mean, I'm not saying that you're not smart. I'm just saying that you perhaps didn't play around with it enough. And the people who got 90-somethings, they will tell you, buy them lunch or dinner or something, or bribe them some or the other and say, how did you get your 90-something? And they will tell you, I did 5, tests, right? And I saw his tricks and I know what he's coming up with. And yes, he knows, I know, and all the good student knows, but the students who didn't do the test, they don't know what is coming. But all of you should know. And when you look at all the whole exams, you're like, there's a pattern here. He's bringing the same thing over and over again, but he's changing it a little bit. And that's what I have to do, because I can't give you things impossible. So this tells you now what I did there is I said there's a loop here before you get into this thing here. You go to this part. So in here, there's a loop in the halfway here. So from here to here, that's where I pick the loop. There's a loop here too, but I didn't care about that loop, right? So you're thinking, man, it's complicated. One time you pick the loop here, one time you pick the loop there. And so now you pick the loop in the second half. Why? Well, because I'm planning to skip it. So if you skip this loop, what happens? You end up with something between 2 perfect squares. You end up between n squared and n plus 1 squared because you skip piece of this 2n plus 1. You're thinking, oh, and then you say, okay, you accept that. If you go here and you skip this, you accept this, and then that cannot be inside the language because the thing is only supposed to take the squares and you get a contradiction, right? So contradicts the fact. And you're thinking, man, this is, that is the idea. So you can summarize these ideas in the last 3 examples as follows. It's called a pumping lemma for the regular languages. And I wouldn't bother to prove it. The reason being we have other fish to fry in the kettle or whatever, other fish to fry in the frying pan. But this is basically telling you the same thing. You get a loop and something happens. So let us look at what it says. Let L be an infinite regular language. So let us underline that. It's infinite and it's regular. So you're thinking, okay, what does that mean? Then we can find a positive integer n, and this n is the same as the n there. It comes from the machine that is equivalent to the regular language, such that every string in omega member of L can be split into 3 parts, omega x, y, z, with the xy less than n and the y greater than or equal to 1, right? The z is the rest. So the idea here is you, in the picture, you run all the way up to Qn, and that is n plus 1 things. As soon as you get n plus 1 things, so here is n plus 1 if you like, the length of the string, because you go from Q0 to Qn, you gotta have a loop. And then you're thinking, I could write this loop forever, and that's what this is all about. It says everything can be split like this, and this is always going to be there. And so you're thinking, oh, okay. So you go here, and then you write this forever and ever, amen, right? So this is what this is all about. And then the Z part, you don't concern, because the Z part is, they might be loops, they might not be loops, we don't care. But the Z is all the rest here plus the part after this loop. So that is why I put Z is equal to from here all the way to there. From the QJ all the way to there. And the Y is from QJI to QJ, and the X is from here to here. And that is why the X and the Y are less than or equal to N. Because this loop has to be somewhere between here and here. So you're thinking, okay, well, what does this do? Well, in the homework, I showed you how to do these problems using the pumping lemma. Now, why is the pumping lemma important? In our course, it's not as important. We just have to know what it says. Why? Because the syllabus says the student should know what is halting problem, what is pumping lemma. The reason for that is when you go to the next course called Theory of Computation, you have to, in Theory of Computation, you have to learn how to do what is called pumping lemma for context-free language. And then you say, oh, so that will prove there are non-context-free languages. Correct. But they will review pumping lemma for regular languages, but they expect you to know it. So they said, hey, that's your job. You teach them that. So I said, okay, I will teach them pumping lemma for regular languages. So that is the purpose of this. Now, using this, you can get proofs of these results again. So that's the second way for proof. But I tell students, look, this thing is bad enough. Do it like I do, and don't, in the homework solutions, I do it like, using pumping lemma. I also do use it without using pumping lemma. And then after 35 years of teaching this course, I said to the student, don't use the pumping lemma. Just memorize what it says, and then that's my job is done. Why? Because the students who use the pumping lemma don't know how to use it, right? So I said, okay, they want me to write pumping lemma down. So this is what pumping lemma says, and this is what you got to learn. So let me put it in bracket. Because in the next test, half the time it says, write down what the pumping lemma for regular language says. The second half says, usually this is question 3 or so, right? Or question 2, it says, write down what the pumping, what the busy beaver function, or write down the halting problem. Those are 3 important things. Busy beaver function, you don't know what that is. Halting problem, you don't know what that is, but these are 3 required things. So I said, okay, I will give that as definition. You memorize it and you write it down. So again, the idea is the same thing. I told you the idea here, but there's no point in wasting time doing it. Now, we can use the pumping lemma to get a contradiction and show that this language, in which the number of A's is equal to twice, number of B's is equal to twice the number of A's, is how you call it, non-regular. So you can use the pumping lemma, right? And I will do that one example, but there are ways of doing things. So I will do it, and as I said, so you can see why is the pumping lemma good. So you say, okay, so this is the language. The number of A's of phi is equal to the number of B's of phi. Now, if you try to get machine and try to get a contradiction directly, it is hard, right? But I don't give you hard things like this. I give you things like, okay, let me pull out a question and show you, because I like to do this so you can see
225
graph theory. You can see what I am giving you. Test 1. I know, test 1. Test 2. Sorry about that. And then you can know. It says this is too small.
Okay.
Okay. Determine which of the following languages are regular. So I usually have something A to the K, such as K mod 3 is less than 2n squared minus 1, and L2 B to the K, C to the N, K is greater than equal to N. So you have a condition here. And so basically it says the number of B's must be greater than, 2n squared plus 1. No, so there's a relationship. Just like how there was with context-free grammar. So you're thinking, okay, let's see what your proof looks like. Your proof looks like the same thing. You say, suppose, you write that, and then you get a loop, and then you skip the loop or write the loop twice, and you get a contradiction. And so you take just this little piece. But I put it for n. And then this one, you write a regular expression, because usually you can write a regular expression for that. Okay, great. You're thinking, oh, okay, and you get 18 points for doing those stupid things. Yes. Now, and here's the point I asked you. Write down what the halting problem asks, right? Maybe in a previous test, I asked about pumping lemma. Pumping lemma, what is pumping lemma? It says, okay, write down the Bezier function. Where is the stupid pumping lemma? Maybe the previous time, right? Because if they don't see me ask the question, they're like, hey, you're not testing them. Oh, busy beaver again. Shucks. Okay, maybe lucky here. No, one more. Halting, always it's halting or what? Or no, it has to be. Okay. I halting. But somewhere, if you look, there is regular. Let me maybe one more I'll try. Say 14. Busy beaver. Okay. I gotta find one. 12. There's too many tests. Pumping lemma. Praise the Lord. Amen. Hallelujah. Okay, write down what the pumping lemma says. So you can see it usually straight direct question like that. You don't have to prove it or anything. And then you can see this is, you do the thing from what we did here, complement reverse. Then we already did this, how you get a grammar and you convert the, okay, you have a grammar, you have to convert it into NFE. Then you have an NFE, you convert it into grammar. So you're thinking, okay, I can do that. And I can do that stupid thing. And I can find this. No, you didn't do this yet. And then this question here, you see, you can do this and this one you can do. So you're like, okay, I can do 1. I can do 2, 3, and then half of this. And then by the end of, this chapter, we'll be able to do 4. And then you have 2 more. You're thinking, okay, I think, the second test, I think I should be able to do okay. So I'm glad I found this test. But, it took a little while. And sometimes, you'd only have covered 3 because, the material you can get, like I put 2 questions in one here. You can get 1 on that, 1 on this, and 1 on that. Something on Turing Machine, something on primitive recursive function, and something on recursive, function. So you're thinking, oh, those are 3 questions. Yes. So sometimes it's 3, sometimes it's 2. So I squeeze it in and I make 2, but I put a lot of points, right? Sometimes I don't want to squeeze it up, make it too big a question, I make it into 2 questions. And then it becomes like 15, 15 or whatever. And this becomes the big question because it's 2 parts, and those will be 1 part, 1 part. All right. So that's that. Let's go back to this. So what is my point here? My point is you can use the pumping lemma, and we will use it today, right, to prove that this guy is non-regular, right? So you're thinking, okay, let me put in this little r here that got cut out, non-regular. Okay, good. Use the pumping lemma for regular language, prove that this guy is non-regular. Now, as I said, this is the only example I gave, but I don't want to, if I didn't give you one, I don't recommend you use pumping lemma. Why? Because it's complicated. And I wouldn't test you, I wouldn't give you a question like this. I would give you the other kinds that can be done directly. The reason being, I'm trying to make life simple. And I think this is, in my opinion, not fair for undergraduate students. It's good for graduate students. But, they told me you got to teach them that. So I will. And then I got to show you how it's used. But, they can't force me to test you unless they say you must give a question. Okay, so suppose L4 is regular. And why do we keep saying that? The reason being, we say this so that we can get a contradiction. Right? Then by the pumping lemma, so you can clearly see it's infinite, L4 is infinite. So then by the pumping lemma, we can find an N1 such that omega is member of L4 if and only if omega is greater than N and can be decomposed like this, right? So you're thinking, okay, you're just writing what the pumping lemma says. Good. Now, here is the point. I get to pick my omega. I said pick omega equal to this. Now, why did I pick this? So you're thinking, wait, you are just doing the same thing you did when you were picking A to the n, B to the n. But here, what you wanted the number of B's was equal to 2 times the number of A's. So you're thinking, okay, you had n A's and 2 n B's. So that is correct. So this guy is in L4. So you're thinking, oh, so if it was number of B's equal number of A's, then it will be A to the n, B to the n will be inside. But it has to be A to the n, B to the 2n, because this number here must be twice this number here, which is correct. 2 of the n here is equal to that. So you're thinking, okay. Now, since the first n characters are all A's, we must have x is equal to this and y is equal to this. Because that's my omega, x, y, z. And the x and the y cannot have length, more than n. So x and y must be part of this. You're thinking, oh, so that's why you pick that to be your omega, correct? And then the z is whatever is left over, right? A to the p, a to the q, a to the n minus p minus q, b to the n. How will we get a contradiction? But by the pumping lemma, x, y to the 0 is going to be in L4. So a to the p lambda times n to the p minus q is times b to the n is this, is in L4. And then you say, but this contradicts the fact that the strings in L4 have twice as many b's as a's. You're thinking, oh, you just skipped the loop. Yeah, but you are not seeing any loop. That's the problem. You are not seeing, like in the previous example, the loop. But basically, I skipped the loop because I could skip the loop, y to the 0, or write the loop twice, y to the 2, or write the loop 3 times. In some homework problems, we have to write the loop many times. So write the loop 2 times, y to the 2, or 3 times, y to the 3. But I skipped the loop. I said, hey, skip that y part. And then you're like, okay, why is this not in L4? Because this is 2n, and you double that, you're not going to get 2n. So you're thinking, okay, and so you get a contradiction. And then if you get a contradiction, it means you're non-regular. And you're thinking, oh, so you didn't have to go through all of that machine. That is why some people like this. Now, if you do it in the exam, I won't kill you. I will say it's okay, but know what you're doing, because it's easy to get it wrong. If you do the other method, and even if you get it wrong, at least you're doing it from scratch and you'll get credit. Here, if you do it wrong, you don't know what you're doing. That's why when people do it wrong, then you won't get much credit because you don't know what you're doing. But if you do it right, then you get the full credit. If you do it wrong, you won't get much credit. But the other one, even if you do it wrong, the fact that you are starting from scratch gives you some credit. But you won't get more than half the credit, of course, because you got to get it right to get all the credit. Now, we can prove other languages are regular by using closure theorem and previous result. So this is not the only way to prove languages are non-regular. So, let's look at this example. Show that L5 is equal a to the k, b to the m, such as k is not equal to m, is non-regular. So you're thinking, man, how are you going to get a contradiction like that? It's going to be difficult. That is true. It's difficult to get a contradiction from this, right? Because how are you going to go and to get a contradiction, you'll have to kind of write some loop and make the number of A's equal to the number of B's. But that's very hard to make them equal. It's easy to make things not equal or make things less. But it's hard to make them equal because this language says, if you want to get out, you got to make the number of A's equal to the number of B's. You're thinking, this is hard. But there's a way. So you say, suppose L5 was regular, right? So you're thinking, okay, you're going to get a contradiction, correct? Then A star minus A star B star minus L5 will also be regular by theorem 6G. So you're thinking, okay, where did you get that from? Okay, it says if this is regular, of course. Regular minus regular is regular by that theorem 6. So you're thinking, okay, I see what you're getting at. You are regular because of a theorem. Okay, I accept. Let me see if this thing is small. Oh, he's not small. But A star minus this, right, is A to the k, B to the k, m, so that this is greater than 0, right? Minus this, which is just this. So you're thinking, oh, this minus this is exactly A to the k, B to the k. Yeah, because the m must be, so if you are, okay, here is the important point. I didn't say the complement of L5. The complement of L5 is a very complicated thing. It has B's in front of A's and so on. But if you take this, A to the n, B to the n, right? A to the any power, B to the any power, and you minus all of this, you minus all of them in which the k is not equal to the m, you end up them k is equal to the m, right? And then you're like, oh, that was a cool thing to do, which is equal to L1, and then which is non-regular. But this is supposed to be this contradiction because this L1 is this, and we said this is regular, but L1 is not regular, hence N5 is non-regular. You're thinking, give us a proof like that, that's very short. Well, no, I can't give you this because this is, too easy to be a proof. But it shows you, if you think, how you can get proofs of complicated looking things. And of course, I don't want to get too much in that, but we will now explore some other properties of regular languages, non-regular languages, because we already know all the properties of regular. Regular is like the nicest. You union to regular, you concatenate them, you star them, you intersect them, you take relative difference, you take complements, everything is regular. You even take homomorphism, it's regular. So you're thinking, what is this homomorphism again? It's like a translation, but not quite a translation. It's like the best word to say is transliteration. So when you have, say, Cyrillic alphabet in Russian, or Hindi alphabet, Devanagari Hindi alphabet, and you transliterate, you're converting it into the Roman alphabet, which we use in English, you're thinking, oh, so literation keeps, the thing faithful. But translation doesn't do faithful job. So as long as you have a faithful transliteration, everything is good. Like when you do a transliteration, if you have a bad word in English and you put, translate it in Russian, it becomes a bad word still, And, if you say, you dog or whatever, whether you say in Russian, you dog, your dog, or you're a dog, it's not good to say you're a dog. All right. Or, you animal, you or whatever. Or, but when you start, getting more sophisticated and you say, I like your spirit. By the time it reaches Russian, it's like, I like your vodka, right? Because spirit is, could be alcohol or could be, I like your mannerism or, spirit is a very complicated word in English. So translation is bad, but transliteration is faithful. So, but we will explore now some non-regular languages. So here is the question. If L is a non-regular language, then L complement is non-regular. And then LR is non-regular. So you're thinking, oh, if you are bad, then your complement is bad. And then when you turn you around, you are still bad. The reverse kind of, right? Because what is LR? LR, you reverse every string in L. And L complement is you take everything that is not in L. That is on the base alphabet. V star minus L. So you're thinking, oh, so let me write this down. What is L complement? L complement is, and I wish I could write fast. V star. And so you're thinking, where did you get your V star from? The V is the alphabet on which L is based. V star minus L. And so you're thinking, oh, okay, I see where you got that V from. Okay. So how do we know this is so? Well, the idea is simple. Suppose L complement is regular. Right? I'm going to get a contradiction. Then by the closure theorem, it follows that L complement will also be regular. So, but L complement is equal to L. So this contradicts the fact that L was non-regular. So you're thinking, wait. Suppose L complement is regular, then by the closure theorem, the complement of the complement should also be regular because it says in the closure theorem part 6e that if you have give me a language, its complement is, and it's regular, its complement is regular. So, but the complement of the complement is just the original, and you say, but L is non-regular. So this contradicts the fact L was non-regular. Hence, L complement has no choice but to be non-regular. Because if it was regular, you get a contradiction. And then some students like, but Professor, I hate these kinds of proofs. Well, yes, you could hate them, but I can't do nothing but that if you hate proof by contradiction. But if you did discrete math and you like it, this is your course. So this is, I don't know, it looks weird here or whatever. Let me just use a whiteout or whatever. Because I don't like that little thing there. Yeah, that looks like L, right, LR, regular. Okay, go back to red. Now, suppose LR is regular. Ooh, Santa Maria. You don't want that. That kills, you know. Suppose LR is regular. Then by again the closure theorem, LR, R will be L, would also be regular. Just like this L complement. You're thinking, okay, but this contradicts the fact that L is non-regular. So again, L's ends must be regular. You're thinking, professor, bring that. I think I can do that. Well, these are the questions that are considered too easy to bring as a question because, you know, I am not allowed to bring like trivial things like this, right? But, you know, if I could put it in, I would have. But these are things you could get in a quiz, but we don't have any quiz anymore because they give us a whole new chapter. So that's why I cut out the quiz. Now, there are certain things that you wouldn't expect, but these are true also. So if L1 and L2 are non-regular languages, right? It is possible for this to be regular. So you're thinking, you mean two bad things can make a good thing? Yes. It is possible for the concatenation to be regular. And it is possible for the star to be regular. You're thinking, but I thought L1 and L2 are bad. Yes, but the problem is, you got to think of, okay, here is the way I tell students. Think of bad as, you know, like if you're regular, you're nice, you know, regular, right? But if you're non-regular, at least some part of you, you could be totally jagged or maybe a piece could be jagged like this. You're thinking, okay, that's what I call bad, right? And then you're thinking, okay, and your complement, you know, let's put a blue for the complement. The complement will be this. So this union, this is everything. You're thinking, if you are bad, your complement has to be bad. If you are bad, your reverse has to be bad. Now, your reverse is another story, but the complement is clearly like the union is everything, all of V star. So the union is nice. But if you are very bad, and you know, your complement will be very bad. But now, if you notice here, suppose this is bad and this is bad. When you join the two, suppose you join U, L complement and L, you're like, hey, two bad things can make a good thing because they cancel out their badness, right? And you're like, yeah. So that is why. So here, I want to give you an exact example. So, I mean, basically I said, L1 union L2 could be regular. How? Okay, let's go and take red again. Well, let us take L1 to be this. We know L1 is regular. Mind that guy is killing my thing here. L1 is this. So that is L1. And then this is basically not the complement of L1, but it's kind of like A, B star, B star minus L1. You know, but this is when K is equal to M basically and K is not equal to M. Right? You're thinking, okay. Then both of these are non-regular. Why? I just proved. This is the first thing I prove as regular, and this is the last thing I prove as non-regular, as an example. This was L5, I call it. But I have to call it L2 here because I want L1 union L2. And then I said, and these are both non-regular. But the union is this, which is regular. So two bad guys can make a good guy. You're thinking, okay, I want to see you do this, L1.L2. So I said, take L1 to be this, and L2 to be this. So L1 is the set of all things a to the square power. And L2 is basically the complement. So, which is equal to L1 complement. You're thinking, oh, you are not a square, and this is, you know, a to the m such that m is a square. Yeah. Okay, then L1, L2 is this. And you're thinking, I don't see that. Okay, let's put it out. Is everything greater than or equal to 2? So this is a to the 0, a to the 1, a to the 4, a to the 9, a to the 16. That's L1. What about L2? Okay, you are not a square. Well, 1 is a square, 0 is a square, so you can't put 0. But 2, 3, 5, 6, 7, 8, 10. 9 is a square, I skip 9. 4 is a square, I skip 4. Now, every number can be written as a sum of a square, right? A square plus a non-square, right? And you're thinking, really? Yeah. I mean, take any number, 17. You're thinking, okay, 17 is a square, right? 3 3 is 9 and 8. You're thinking, oh, I thought you would say 16 plus 1. No, I don't have 1 here. I only have 2. Take something like 23. You're thinking, okay, 23 is, the whole idea is, if the thing is a square, right? So if it's like, okay, how should I put it? Let's take 23. 23 is not a square, right? So you're thinking, okay, 23 will be here, right? So 23 times whatever here, that works again too. And if the thing is a square, you're thinking, okay, how can you get a to the 25, right? Okay, because you don't have 0 here. And you say easy, you go to the next, right? So you're thinking a to the 16, right? That doesn't work. A to the 9, that doesn't work. A to the 4, it works. So you take the a to the 4 because, 25 can be 4 plus the 21. A to the 21 is somewhere in here, a to the 21. And 21, but you got to be careful because, it's not obvious. That's why I'm spending time on it. You're thinking, okay, so every square number, right? Because not every number, every square is a sum of 2 squares. Like 49. 49 is not the sum of 2 squares, but 25 was particularly difficult because 25 is equal to 3 square plus 4 square. So you can't say, okay, you wouldn't find 9 here or 16 here. But 4 plus 21, this 4 plus the 21 makes the 25. You're thinking, okay. And then if you are like, say, 47, 0 plus 47 here is 47. And you're thinking, okay, 47 is not a square. So you're thinking, okay, I got everything. So you're this, right? And then you're thinking, okay, so the L1 dot L2 is equal to A star. And that is regular because I give you a regular expression for it. Then the last guy is this thing star. This is equal to L1 is this, then L1 star is equal to A star. So you're thinking, how do you know that? Well, basically, every number, right, you only need 1. Every number, right, can be written as a sum of 1s, right? Because what you do, you want to say, this has a to the 1, and then you want to take L1 star. L1 star will have every power of A1. A1 squared, A1 cubed, A1 fourth, A1 fifth. So if you want 97, A1 to the 97. You're thinking, just because you got A1, so anything that contains A will contain A star. And then you can't get any bigger than that. So you think, okay, A star is equal to this, which is a subset of this, which is subset of A star. And you're like, so this guy is, A star is this, right? So you're thinking, I didn't quite get what you said here. Why? Okay, let me just, again, go down. This is the end, of course. But I wanted to push it up a little more. I said A star is equal to, let me clean this up. Sorry about that. Because it looks like a D, no? Okay. Yeah. Man, that's the stray marks that come. So I got to be careful here. So you're thinking, what did you write here? A underline star is equal to A singleton star, because that's what the underline means. You're thinking, okay, those two are equal, I agree. And then what did you say here? I said, this is a subset of this. Why? Because this here contains A, right? And so this thing star, if L1 contains L2, L1 star is subset of L2. That's one of the theorem we proved in the very early stage in chapter 1. So you're thinking, okay, that star contains this star because this has an A. Okay. Then I said, this is a subset of A star. So you're thinking, why? Why is this subset of A star? Because these are just A's. You can't get anything more than A's. You're thinking, okay, I agree. So this is subset of this. That means all of these guys are equal because this is equal to this. These two are equal. So this gets squeezed between two equal things. This has no choice. Red ink. This has no choice but to equal. I hate that. This has no choice but to be equal. So now you get that. And you're thinking, okay, I see. You can get two bad things making a good thing, two bad things concatenating to a good thing, and a bad thing, multiplying to a good thing. Can you get two bad things also intersecting to a good thing? Yes, but I didn't want to say that because, okay, you could have a bad thing here, right? And you could have another bad thing here. But the intersection is nice, right? So I could put this for difference and whatever, but these examples illustrate everything. So it says, if you got bad things, like I don't like to give analogies because they're not perfect, but when you're thinking of these things, right, the analogy that you should think about is like, sometimes you've seen it, some guy has some very long nose, the guy is big and ugly or whatever, and his wife is also not that good looking, but some or the other, they get beautiful children. You're thinking, man, their negatives cancel out. He has a long nose, she has a short nose, and or whatever. And it works out to be a child has a beautiful nose. So that's like two non-regular becoming regular. But the analogy is not perfect because human beings are complicated and life is complicated. But sometimes that happens, and two ugly people get nice children, and I'm sure you probably know somebody like that. So whatever it is, the intersection of two ugly things can be nice. The complement of the relative complement could be nice, but not the full complement, right? Because the relative complement, suppose you have this, and then you have another set here, and you say, I want this guy minus that guy. You see, this guy is nice, it's smooth, and it's not got any problem. So this is, okay, this jagged thing is like an aid to your memory. It doesn't mean this is a proof, right? But it is a way for you to think about it. And you like, when you think about odd numbers, you're like, okay, it's, but if you want to prove something about odd numbers, you have to say it's of the form 2k plus 1. Even numbers are of the form 2k, and then you prove. But you're like, odd numbers, they're funny looking things. And so this is like a mnemonic device, if you like. But whatever it is, this is that. Now, I have 10 minutes more. And, I would, if you want to see me this afternoon to discuss anything, please tell me, because I want to go and try to grade those introduction to advanced math people tests, because that I have, spent the whole weekend grading the other two tests. And I barely finished last night. So I want to give them back on Thursday. So I want to start right after this. But if you need to see me, you are important too, so tell me. Now, I want to, so let me just save this. Save. And I save it on my desktop. So whatever things I put, I save. And then I want to go back and look ahead because I got 10 minutes. So I am going to look ahead now and go back like this. Instead of looking back all the time, I usually look back. I look at chapter 5. And we won't be able to, do much in chapter 5 today because we only have 9 minutes left. And I don't want to keep you, but I don't want to throw those 9 minutes away. So we did chapter 1 to 4, and it was all about, we started. So let's go back again and see, we started. Languages and regular expression. You're thinking, okay, I got what you said, and make it a little bit bigger. Okay, so languages and regular expression. You're thinking, yeah, I am tired of your regular expression. I hate those things. By the way, I am surprised at the number of people who got the regular expressions wrong, but I keep thinking, all I did from the last test was switch the two things, the zeros and the ones, right? For the first part. And then the second part, I said exactly two Bs, two BBs, right? Two occurrence of BB. So I already did this when I was doing 0, 0. So I'm thinking, this is not anything strange. You've seen this. And you can, again, you can expect this because I tell you, one, I will give you, the order is important, and then you got an overlap part, and you will get 4 pieces. Usually, sometimes you get 3, but most of the time you get 4. So you've got 19 tests like that. So everybody should have gotten number 2 right. And then you're thinking, oh, but professor, I didn't remember that stupid thing. But I tell you, I won't bring 3. I will bring either at most 1, exactly 1, or exactly 2. I mean, I can't make it any simpler, right? And I mean, so there's not much to worry about there. It's like clear cut. Okay, you've seen all the tests, and everyone is just like that. And the only thing I can do is change the letter A and B to 0 and 1, or B and C, and that's the only thing to make it different. But the ideas are the same. And so I didn't understand why so many students got number 2 in the test wrong. And I'm thinking, but that number 1 is a gift. Number 2 is give. No, most of them, that's why people got 90 something, 8, 6 got. But I didn't understand that, but maybe somebody could tell me why they didn't expect that question, and why, even though they saw it's like exactly 2, they didn't, get it right. Because you know what to expect, you got to practice. So let's go back and look. Languages and regular expression. So you're thinking, okay, those are that stupid thing about, 2 occurrences of BB or 1 occurrence of AA or whatever, exactly 1. And then languages, that's number 6, prove some property of languages. This is subset of that or not. Then we talk about phrase structure grammar, which is, like number 5. You're like, oh, okay, he showed us a technique to get complex free grammar. Yeah, I think I understand that. Then finite state machine. We can find finite state machine, minimize them. We can find machines for modulo arithmetic, and then we can find, the machine for the complement. You're thinking, okay. And then we didn't get to chapter 4, basically. We didn't do non-regular languages. We didn't do convert machine to grammar, grammar to machine, convert, by the way, we did that. Convert, using that GFA. I forgot we did that. When we were doing, you give me a machine, and that was number 2 in the exam. You convert that machine. So actually, we can do 4 questions from the exam now. We convert a machine into a regular expression. And a regular expression you can convert into a machine too. So all of that we did in chapter 4. And then in chapter 5, this is where the thing gets complicated. And then you got chapter 6 and chapter 7, right? So chapter 5 and 6, these are the hard chapters. Chapter 7, they told us to add that one. And then chapter 8, which is not included in the course, but some universities do it. I thought I should tell you that they do it. But our thing is they want us to do this. And I would rather they do this. Because why? This is relating machines to context-free grammar, which is, and then you can hear about, context-free grammar, pumping lemma. But they don't want us to do this, they want us to do that. So I said, okay, we have to skip that. I got to obey them. So this is what we're going to do, Turing machines. And now, what are Turing machines? Basically, Turing machine is, in some sense, the theoretical model on which your computer is based. But there is a difference. The Turing machine is infinite. Your machine, it has finite memory. The Turing machine has infinite memory and infinite space. Your machine has limited storage, limited, memory. Active memory that is the RAM, random access memory. And so, what is a Turing machine? So this is the key point for me to get through, and then I will stop at 350. The key point is that the Turing machine is they have a simple, long, infinite tape, and it's better to make it 2-way, but you can make it 1-way because you could say when you reach that, symbol N, you stop there. But it complicates matter, and that's why you make it 2-way infinite. It's like the real number line, and when you have integers, it's 2-way infinite. The natural numbers are 1-way infinite. But the integers, you have minus going to infinity, plus going to infinity. And you're thinking, okay, 2-way infinite is better. Why? Because there is nothing to stop you. Because when you reach 0, you can't go to the left of 0. But here, you can go to -1, -2, so you can call your tape squares, the number 0, -1, -2. So these are the squares. And then you put things on the squares. So a Turing machine is a semtuple where Q is a finite set of control states. So this is the thing that makes it finite. It has a finite control states, like it can go into only certain modes, and then those modes will be finite. So okay, you have a Turing machine with 10 states, or you have Turing machines with 100 states. So the bigger the number of states, the more powerful the machine is. but it has a finite number of states. That's the key point. But a tape is not finite, because you are allowed to go infinite. And this was invented in 1936 by this guy called Turing. That's why we call it Turing Machine. So you have this tape, and the finite number of states, that's Q. Q is the finite set of control states. What else do you have? T is an alphabet, which is also finite. Everything has to be finite, except that the place for you to work, you don't want to run out of space. So you have unlimited paper, right? So you have a finite number of control states. Then you have the alphabet, which is called the input alphabet, right? And then you have another alphabet, which is called the tape alphabet. So you're thinking, why do you need two alphabets? Okay. You see, on your computer, you can input certain things in your keyboard, but your computer has also certain things. Like you can even include a space, but your computer will have things that, you cannot input, right? So you're thinking, what are those things, right? Well, for example, you cannot, when you input any character or space or whatever you have, G, H, uppercase G, or 0 or 2, the computer converts it into an Ascii code, a sequence of, 8 zeros and ones. So you have 256 of these guys, and each one, you can assign one or a, these are called the Ascii code. So a sequence of 8 characters, which could be zeros or ones, and these you call, your byte. So you get each, input is assigned one of these, right? But you can't input the character 0 or the character 1. When you put 1, that is a different thing. You're putting 8, zeros and ones. So you can't input 0 and 1. So 0 and 1s are part of the thing of that thing, right? And what you can input is like alphanumeric, is 0, 1, 0 to 9. And then you can A to Z, capital A to Z, and then diacritical marks, comma, question mark, brackets, etc. All of those have Ascii code. So you're thinking, oh, okay. The input is different from the tape alphabet, right? But the tape alphabet has to include the input because it has to understand what you do. So it's like, okay, then you have to have a start state, initial state, just like how we have. So basically, Turing machine is like a finite state machine, except that it gets to write. So it has a read and a write. It gets to write and read. And then there's a special character, which we call, well, I don't want to call it a blank, but in your computer, in my keyboard, there's a space bar. So that is not quite the same thing as a blank. A blank means there is nothing there. So your space means there is something here, space bar. But a blank in the Turing machine means, like when you say all of this is blank. It means there is nothing there, but there's C. And so you got to distinguish between a blank and the space bar blank, because both of them are called blank, but one is a character and one is a symbol to indicate that there is nothing there. And that's part of the tape alphabet to say, hey, there is nothing there, but it's not part of the input, right? And then you have a designated accepting state, just like NFA and DFA. And then you have a relation to say, if you are looking at something and you're a particular state, what do you do, right? And so here is the Q to tell you what your state is. And then this is the I seeing what the guy is. You're thinking, okay. So after this, I will stop. So if you're in state Q and you give me an input A, right? You're looking at A, then you will go to Q prime and B and you'll move right. So that's how the instruction will look. So this means if you're in Q and you see an A, go to Q prime, change it into a B, and then move 1 square to the right. You can also move 1 square to the left, right? So instead of light. So those are your 2 options. So we usually write this as Q, comma A goes to Q prime B R. Or better yet, Q, if you see an A, put a B and then move right. And this is the best notation, right? And that's what it means. And I will stop here, and in the tape, I will show you, you're in Q, you look at the A, right? You replace the A by a B, and then you move 1 square to the right, and you go on to the D, and you look at the D, and then you do what the D says, but you take your instructions from Q prime. So you say, hey, I'm in Q prime. What do I do when I see a D? Because if you're in Q and you see a D, it's a different thing from in your Q prime and you see a D. And the next time we come back, I will run through a machine for you, but I wanted to give you a little introduction here and start off this chapter. So we only did one page. Okay, those of you, if you have questions about your test, you can ask, but, I wanted to start grading the other people's tests. So if you want to tell me, that you're coming, it's okay. I take a break and eat something, and then I'll be back at, 3:30 or whatever. But tell me if you're coming so that I can know and not start, because I don't want to start and stop and things like that. All right, so you guys take care, and I have one more thing to do. You have a nice day and good luck. And as I said, don't panic about your first test. If you got over 50, like one student who I think they got 50 something, they were like, Professor, I did badly. No, I think, one reason the student got 56 is they probably didn't do 5 exams. Because if you did 5, you wouldn't have gotten 50 something, right? So whatever you got, don't panic as long as it's more than 50, right? But if you get less than 40, then my recommendation will be for you to drop. Because why? I have never had any student, it is not possible to recover from such amount. And then we can play games. We can say, okay, you have 3 exams, I will drop all and accept 1 exam, but then I will get in trouble. And there will be complaints against me, I mean, I get complaints. Why? Because I teach the ugly courses. And then if I do anything like drop the lowest test and it's not written my syllabus, they can sue me, saying, hey, you did that and I don't like that, whatever. So I just add your 3 scores, you get 216, which is not impossible. It's only 60%, you pass. You don't get 216, you don't pass. And if you get 212 or 214, I'll pass. But I can't let you pass with, 180 or 170 or whatever. That's too low. That's way less than 50%. All right, take care, good luck, and God bless.